Good morning students. Today our class is about applications of the Gauss law. Already we learnt about the electric field which is due to point charge by using the Gauss theorem. Okay. So now that is the point charge. Now we have to know when the charge is distributed over the surface, then we can find the electric field that is used by the Gauss law. Okay. So by using Gauss theorem, we can find the electric field due to what? The charge which is distributed on the surface. Okay. So if it is the charge is distributed on some conductor, then we can take in as charge enclosed as the linear charge density with some length L, and also if the charge is distributed on some area, then we have to use areal charge density, and if charge is distributed over the volumetric surface, then we can use volume charge density. Okay. So now I am considering the charge conductor. Okay. So that is the charge is distributed on the conductor. Okay, long conductor. Okay. So now I want to find electric field due to a long conductor. Okay. So here by using what? Gauss theorem. Okay. Now see here. This is my conductor. So here the charge is distributed over this conductor. Okay. Now due to this conductor, I want to find the electric field at some point. Okay. So here I am taking one point here. So this is a point P. Okay. At this point I want to find the electric field. Okay. So here due to this charge the electric field is different, due to this charge the electric field is different, due to this charge the electric field is different. So here to get the complete charge on this conductor, here we are not using the total charge. Okay. Why? Because here we are not using the term total charge. Why? Because here the charge is distributed over the length of the conductor. Okay. So here this is a conductor which is having some length L. Okay. So now in this situation we have to use the term, so the charge per unit length. Okay. So charge per unit length is what? Lambda. So this is the linear charge density. Okay. So here we are not using the word, so that is the total charge, because here the charge is distributed over the length. So that's why for 1 meter length the charge is lambda. Then for L meter length of the conductor, how much charge is there? Okay. So the charge is equals to what? Lambda into L. Okay. Now see here, this is the conductor. So here charge is distributed here like this, and I want to find the electric field at this point. Okay. So first by using the Gauss theorem, already we learned what is Gauss theorem. Gauss theorem is what? Which gives the relation between the electric flux and the charge enclosed. So the total electric flux is equals to what? The integration over the closed surface and E dot ds. Okay. So these two are vectors, and in those two vectors here we are having the dot product. So that must be is equals to what? Q enclosed by epsilon naught. Okay. So this is the Gauss theorem. Okay. Now here by using this Gauss theorem we have to find the electric field. Okay. So for that just we have to follow steps. Okay. We are having so 4 steps. No, the first step is what? First step is we have to consider a Gaussian surface. Okay. We have to consider a Gaussian surface. So Gaussian surface means what? It is a closed surface and imaginary one, and E and theta must be symmetrical. Okay. So E and theta must be symmetrical at every point. Okay, on this Gaussian surface. Okay. So now first we have to consider a Gaussian surface. Okay. So this is a long conductor. Here the charge is distributed like this. Okay. Now I want to find the electric field here. So here at every point on the our assumed surface, every point the electric field must be same and the theta also symmetric. Okay, now here if I choose any sphere, okay, so if I choose any sphere as a closed surface, let us consider I am choosing the sphere. So this is my sphere. Okay, so this is my sphere. Let us just consider like that. Okay, so now see here, this is the point P, no? Okay, so here to here the distance is r. Okay, so here to here the distance is less than the r, and here to here the distance is less than the r and less than the r. Okay, so that means here as r is varying, okay, so here r is varied, so then electric field also varies. Okay, so that means if r changes, then electric field also changes, because already we know that from the Coulomb's law, electric field is inversely proportional to the square of the distance. Okay, so as electric field is inversely proportional to the square of the distance, as r changes, then electric field also changes. So that's why here we are not considering the sphere as a Gaussian surface here. Okay, so now let us consider this is a long conductor here. Okay, so now this long conductor having some length L. Okay, now here I am considering the another Gaussian surface. So here is my point P. Okay, so that Gaussian surface must be passes through this point. Okay, so now here I am considering the Gaussian surface as the cylinder. Okay, so here I am considering the Gaussian surface as cylinder. Okay, so this is my Gaussian surface. Okay, now see here. So first condition is what? This is an imaginary surface. Okay, and second one is what? It is a closed one. Yes, here top and bottom both are closed, and at every point from all the sides, so the cylinder is closed. Okay, so now this is the closed surface. And next one is electric field and theta must be symmetrical. So electric field, now here is a point P. Okay, so from here to here the distance is r. So here we are getting the electric field somewhat. Okay, so here to here the distance is r only, here to here the distance is r only, from here to here the distance is r, here to here the distance is r, here to here the distance is r, here to here the distance is r. So here r is same at every point, same at every point on the curved surface. This is a curved surface, no? On the curved surface of cylinder. Okay, so as r is same, so here the electric field also same. Okay, so electric field also same. So electric field is what? Symmetrical. Electric field is same. Okay, so now see here. So at the curved surface r is same, but at this point here these are the two flat surfaces of the cylinder. Okay, so these are the two flat surfaces of the cylinder. Now see here, this is the charge conductor. So here the electric field is in this direction, this is the electric field direction, and this is the electric field direction. Okay, now from okay, as here the charge is there. Okay, charge is distributed like this. So this is like just bottle brush. That means at all sides we are having some field lines like this. Okay, so see here, this is the electric field line. Okay, now as it is a electric field line, so this is the surface. Now always the area vector is normal to the surface. Okay, so now this is the surface. Now the area vector is, now just take here a small area. So now this is the ds. Okay, now the angle is what? Theta is equals to 0. So let us consider here is a small surface. So here this is an electric field direction, and this is the area direction. So here also theta is equals to 0. And here just consider a small surface, and this is the electric field direction, this is the area vector. So here also theta is equals to 0. Okay, now at this time in this side also, here is the small area, and this is the electric field direction, and this is the area direction. So here also theta is equals to 0. Okay, so on the curved surface, so right on the curved surface, so at every point, curved surface means this side and this side, these two are flat surfaces. Okay, so at every point here the electric field is symmetrical, so that is same, electric field is symmetrical. Why? Because R is same. Okay, now here theta is also symmetrical, because here theta is equals to what? 0 degree. Okay, so that is theta is equals to 0. Now here we are having another surface, so that is a flat surfaces. Okay, so here, okay, on the flat surfaces, see here, this is a flat surface and this is a flat surface. So here this is the conductor, so this is an electric field direction. Okay, now here also this is an electric field direction, so at this side also this is the electric field direction, at this side also this is an electric field direction, but area vector is always normal to the surface. So this is our flat surface, so normal and outward. So if you are taking the some small area element here, so this is the area vector, so we can take it as ds. Okay, so ds, and this is the E vector, so here we are getting the angle theta is equals to what? 90 degree. Okay, so here also this is the electric field vector and this is the area vector, that is the ds. Here also we are getting the 90 degree. Okay, so that means at flat surfaces, of cylinder, so like this is the cylinder, here is the conductor, like this. Okay, so this is an electric field direction, and this is the our flat surface, this is also our flat surface. Let us take a small area element, so always the area vector is always perpendicular to the area. So this is the flat surface, so perpendicular vector is this one, so this is the ds, so here we are getting the 90 angle. So at flat surface of the cylinder, at every point, okay, why here we are using the every point? Because see here, if we are considering this is the small area, so this is the vector, area vector, and from here we are getting the electric field vector, so this is the electric field vector, so here also we are getting the 90 degree. If you are considering here is the area, small area, so this is the ds vector and this is the electric field vector, so here also we are getting the 90 degree. If you are considering this is the small area and this is the ds vector and this is the electric field, if here is the small area and this is the ds vector. Okay, so that means at every point on the flat surface, electric field and the area vector both are perpendicular to each other, so there exists an angle theta is equals to 90 degrees. At every point the theta is same on the flat surface. At every point theta is same on the curved surface. At this curved surface we are getting the, if this is the electric field vector and here is the area and this is the area element, so here theta is equals to 0. So that means at every point on the curved surface theta is equals to 0. Theta is symmetrical. At every point on the flat surfaces, we are getting the theta is equals to 90 degrees. So this is also symmetrical. So here at every point E is symmetrical. Okay, and theta is symmetrical. So at flat surface theta is equals to 90 degree. Okay, so here now as theta is equals to 90, so then phi is equals to what? E ds cos theta. This is the magnitude. Okay, so now if theta is equals to 90 degree, then cos 90 is equals to what? 0. Okay, so as cos 90 is equals to 0, then total flux through flat surfaces, what? E ds into 0, so that is the 0. So now for the cylinder, the flux through the flat surfaces is 0. Okay, so now just here we have to find the flux through the only curved surfaces. Okay, now here this is the first step, which is about the Gaussian. We are considering one Gaussian surface which is the closed one, which is symmetrical. E and theta must be symmetrical. Okay, so I am considering the Gaussian surface as the cylinder, and at every point E and theta is symmetrical. Okay, now second step is what we have to find the that is flux. Okay, so step 2. Okay, step 2 is what? So we have to calculate the closed integral E dot ds. Okay, so for this let us consider E closed integral E dot ds is equals to what? Here this is the electric field is symmetrical. As electric field is symmetrical, so here we have to write this as what? The closed integral over E ds cos theta. Okay, so this is a vector form and this is a scalar one. Okay, now see here, this is the E is the same, E is constant, because here E is symmetrical. Already we taken this one. Okay, so now this can be written as, here we are having the three surfaces. Okay, so one is curved. Okay, so that means here we are having the curved surface and upper flat surface and bottom flat surface. Okay, we are having the three surfaces for this cylinder. Okay, so now here for the total integration over the closed surface E dot ds can be written as, so the flux which is through the curve. So here we are not taken a closed integral, we have to write just integral E ds cos theta, that is for curved. And now next E ds cos theta, that is only for flat, which is upper flat. And now E ds cos theta, which is the bottom bottom flat. Okay, now see here, so here we are only getting the flux which is due to curved one. So the integration over E ds cos theta and the curved. Okay, so here due to the flat surfaces we are getting the flux is equals to 0. Why we are getting flux is equals to 0 at the flat surfaces? Because here we are taken that theta is equals to 90 degree. So as theta is equals to 90 degree, cos 90 is equals to 0. So that's why it will become 0, it will become 0. Okay, so the flux through the flat surface is 0. So here 0 plus 0. Okay, now here the electric field is symmetrical, so just it is a constant at every point. So just taken out E and now curved, so that is ds. And here at curved surface theta is equals to what? 0. Okay, so at curved surface theta is equals to 0. At curved surface the angle between the E and ds is what? 0. So as theta is equals to 0, cos 0 is equals to what? 1. Okay, so here cos 0 is equals to 1. Okay, now okay, plus 0 plus 0. Okay, so now E, so this is the surface integral of the curve. Okay, so this is the surface area. Okay, so the cylinder surface area is what? 2 pi r l. Okay, so now this is the closed integral over E dot ds. Okay, so now second step is over. Now third step is we have to find the charge enclosed. Okay, so that is the charge which is enclosed by this Gaussian surface, the charge which is enclosed by this Gaussian surface. Okay, okay, now third step is, step 3 is what? We have to calculate charge enclosed. Okay, charge enclosed. Okay, so now charge enclosed within the surface. Here we are considering the cylinder. So and we are having the charge which is distributed on the length of the rod. Okay, so which is having some length of the rod. Okay, so for 1 meter length the charge distribution is lambda. So this is known to be a linear charge density. Okay, now but here we are having the length of the conductor, so that is L. For L length of the conductor, what is the charge? Okay, so now the charge is equals to what? Lambda into L. So this is the charge enclosed. Okay, now step 4 is what? We have to apply Gauss theorem. Apply Gauss theorem. Okay, so Gauss theorem is what? The closed integral over E bar dot ds bar is equals to Q enclosed by epsilon naught. Okay, so E bar dot ds bar, from the second step we are having E into 2 pi RL, and that must be is equals to Q enclosed is what? Lambda into L, so that is epsilon naught. So L and L are cancelled. Then here we are having E is equals to lambda by 2 pi R epsilon naught. Okay, so this is the electric field which is due to, this is the electric field due to long straight conductor. This is by using Gauss theorem. Okay, so now we have the another application. So that is the electric field which is due to the long sheet. Okay, so that is the infinite sheet. If you are considering the infinite sheet, then so by compares to the R we have to take. Okay, so okay, so now second application is what? The electric field due to large sheet. Electric field due to large sheet. Okay, so now here already we learned that if here is the sheet which is the infinite sheet. Okay, no, it is the infinite sheet. Okay, so for this infinite sheet the charge is distributed like this. Okay, so for this sheet we are getting the electric field lines are which are parallel field lines and those are uniform. Okay, so here we are getting the electric field lines. So like this, these are the electric field lines. So here these are the uniform electric field lines. Electric field. Okay, so uniform electric field means they are not intersect. Okay, so all the field lines are which are parallel. So field lines are parallel lines. Okay, now here this is a surface. So here sheet is a surface which is the 2-dimensional one. So here we have to use the areal charge density. Areal charge density, so that is sigma. Okay, now here we have to, so first here the charge is distributed over the sheet, infinite sheet, but here we are using the term, so that is charge per unit area. Okay, so this is the charge per unit area. Charge per unit area, so that is the areal charge density. Okay, we are not using the term total charge. Why? Because here the charge is distributed over the area, so that's why here we are not using the term total charge, we are using the term charge per unit area. Charge per unit area. Okay, so now here I am first step. The step 1 is what? We have to consider a Gaussian surface. Okay, so it is a closed one, and also E and theta must be symmetrical. E and theta must be symmetrical. Okay, so for this, now here this is the sheet. Let us consider so this is the sheet. Okay, so okay, this is the sheet. Okay, so now if it is a sheet, if this is the sheet, from the side view the sheet is like this. From the side view the sheet is like this, and this is the electric field lines. These are the electric field lines. Okay, so So if this is a sheet, the charge is distributed over this sheet like this. This is the charge distributed on this sheet. Okay, so now as it is an infinite charge, from the side view the sheet is like this. Okay, so this is a sheet. From the side view the sheet is here, as this is a charge distributed on the sheet. So this is the electric field which is outward like this. So this is the electric field lines. Okay, so these are the electric field lines. Okay, now here, so from the side view I am taking the sheet like this. So okay, so this is my sheet. So this is my sheet now. So the charge is distributed like this. This is the charge distributed on the sheet. Okay, so here I want to consider one Gaussian surface. Okay, so if I consider the Gaussian surface as a sphere, if I am considering the Gaussian surface as the sphere, so again the R will be changes. Okay, so if I considering the Gaussian surface as the cylinder, okay, like this, if I am considering this Gaussian surface as like this. Okay, so here also we are not getting any correct one. Okay, why? Because if this is the sheet, this is the sheet, this is the field lines, so we have to consider the Gaussian surface, so which is covering the charges. Okay, which is enclosing the charges. So that's why here I am considering the Gaussian surface as a cylinder, but the axis of the cylinder must be here. This is the cylinder I am considering, but the axis of the cylinder must be through the this one. Okay, so here this is my Gaussian surface. Okay, so the axis of the cylinder must be perpendicular to the like this. Okay, so this is my sheet. So this is my Gaussian surface cylinder. Okay, so this cylinder must enclose the charge inside. Okay, so in the before case, if you are considering the long straight conductor, if it is a long straight conductor, so in this case we are not considering the Gaussian surface like this. Okay, we are considering the Gaussian surface along the axis of the conductor. Okay, so this is the axis of the conductor, no? So that's why along the axis of the conductor, here we are considering the Gaussian surface like this. So this is my sheet. So the axis of the sheet is like this. So we have to considering the cylinder like this. Okay, so now this is my Gaussian surface. Okay, so now, so this is a closed one. Okay, so now the electric field must be symmetrical at every point. Okay, so see here, first for the cylinder we are having the two surfaces. Okay, okay, so this is a curved surface, this is a curved surface, and this is a flat surface. Okay, so now first consider a Gaussian surface which has symmetry. Consider a Gaussian surface as cylinder which has symmetry. Symmetry in what? Symmetry in E and theta. Okay, so here this is the for any sheet. Okay, for any large sheet, for any sheet, here the electric field lines are uniform. Okay, so these are the electric field lines which are uniform and parallel. Okay, so here I placed one Gaussian surface. Okay, so see here we are having the two surfaces. Now first this is a flat surface. Okay, so as this is a surface, now these are the electric field lines which are passing through this surface. So this is the electric field direction. Now this is the area. So just consider area, small area. So this perpendicular to this area we are having the area vector. So here we are angle theta is equals to 0. Okay, so just consider here is the small area. So this is the electric field vector. So the area which passes through the area vector is like this normal. So this is the E. So there is angle theta is equals to 0. So at every point on the flat surface, so here we are getting the theta is equals to 0, and E is uniform, E is symmetrical. At this point E is same, at this E is same. Okay, now at left side, see here. So this is the electric field direction. Okay, so here electric field direction is in negative side. Okay, so now this is the area, so I am considering one small area here. So this is the electric field which is coming out from that area, and here this area vector is what? This is the ds vector. So here we are getting the theta is equals to 0. Now if this is the electric field vector, so here we are considering a small area, and this is the area vector. Here also we are getting the theta is equals to 0. Okay, so here E has a negative direction and the area vector also having the negative direction. So product of those two we are getting the positive only. Okay, so now at the flat surface is over. Now here this is a curved surface of the cylinder. So at the curved surface, so as this is a surface, so this is a charge. Okay, now this is the electric field vector direction. Okay, here this is the electric field vector direction. Now here I am considering one small area on the flat curved surface. So the area is like this, the area vector is like this, which is perpendicular to small area. So this is the ds. So here we are getting the angle 90 degree. Okay, so that is theta is equals to 90 degree. Now as this is the electric field direction, now here I am considering one small area. So area vector is perpendicular to area, so this is ds. So here we are getting the 90 degree angle. So theta is equals to 90 degree. Okay, so that means at flat surfaces, at flat surface of cylinder, electric field is same. Okay, E is symmetrical. E is symmetrical at every point on the flat surface. Okay, now theta is what? Theta is also symmetrical, then theta is equals to 0 degree. Okay, now here at curved surface, at curved surfaces, so at every point E is symmetrical, E is same. Okay, E is symmetrical, and also theta is also asymmetrical, but theta is equals to 90 degree. Okay, so now we have to write second step, step 2. Okay, step 2 is what? We have to calculate E bar dot ds bar. Okay, so that is the integration over closed surface, E dot ds is equals to what? So this is the closed surface. No, here in the closed surface we are having the two curved surfaces, two flat surfaces, one curved surface. Okay, so this is a curved surface. Okay, so this is the right side flat and this is the left side flat. Okay, now so this is the integration over curved surface. So that is E ds cos theta plus integration over flat. This is the right side flat and E ds cos theta. Now this is the flat surface and which is at the left side, and E ds cos theta. Okay, now so through the curved surfaces, see here this is a curved surface. No, so along the curved surfaces theta is equals to 90 degree. Theta is equals to 90 degree ante cos theta is equals to 90 degree. So cos 90 is what? 0. So that's why it will becomes 0. Okay, so now at flat surfaces we are having theta is equals to what? At flat surfaces we are having theta is equals to 0. So here theta is equals to 0 means cos 0 is equals to what? 1. Okay, so as cos 0 is equals to 1, so here we are getting the flat surfaces cos, so that is EDS plus now flat EDS. Here cos theta is equals to what? 1. Okay, now so place, so this is E is constant, E is symmetrical at every point, so just taken out E next integration over ds plus E integration over ds. Okay, now so 0 place this is E, this is E, E plus E, 2E. So integration over ds means here we are having the sheet. So for the sheet we are having the area. So that is the total sheet area, let us consider A. Okay. So then E into A plus E into A. Okay. So now here we are having the closed integral E bar dot ds bar is equals to 2EA. Okay, so this is the second step. Okay, now third step is we have to find the charge enclosed. Step 3. Calculate charge enclosed by Gaussian surface. Okay, so now, so that is Q enclosed. Okay, so here we are using the sheet. Okay, here we are using the sheet. So that's why the charge which is enclosed by this sheet must be depends on area of the sheet. Okay, so that's why here we have to use the areal charge density. So for 1 unit area, let us consider the charge is sigma. Then for total area, for complete area, then what is the charge? So that is equals to Q is equals to what? Sigma into A. Okay, here sigma is what? Areal charge density. So this is a Q enclosed. Okay, Q enclosed. Okay, now fourth step. Now fourth step is, so we have to apply Gauss theorem. We have to apply Gauss theorem. So Gauss theorem is what? Total integration over E dot ds is equals to Q enclosed by epsilon naught. So E dot ds is equals to, in the second step we are having 2EA. So Q enclosed is what? Sigma into area. So that is areal charge density into area, that is by epsilon naught. So here E is equals to what? AA cancelled, and here we are getting sigma by 2 epsilon naught. Okay, see here we are getting some one. Now here for the sheet, if I am changing the R, okay, so that means if this is the sheet, let us consider here this is the sheet. Okay, now my electric field point is, this is the charge distribution. So I want to find the electric field here. Okay, so which is at distance some R. Okay, now I want to find the electric field at this point. Okay, so at this point, that means at the Q point. Okay, so this is R1 distance, let us consider this is the R2 distance. Okay, so now here this is the electric field E2, this is the electric field E1. Okay, now there is any variation in the E1 and E2? So the answer is no. Why? Because here the electric field which is due to E field, which is due to sheet independent of, here this equation is not depends on R, so independent of R. Okay, so here compares to the size of the sheet, if we are taking the R, okay, then if here is the R, so I want to find the electric field here. Okay, then also there is no change in the electric field due to this sheet. If here is the my point, so I want to find the electric field here, which is at the distance some R4. Then also there is no change in the electric field which is due to sheet. Why? Because the electric field due to sheet is independent of the R. So that's why the electric field at every point is same. Okay, if it is an infinite sheet, if it compares to the R, if it is an infinite sheet, then at every point, so the electric field is same. Okay, so this is the important point which is for the sheet. Why? Because let us consider this is the sheet. So here this is the sheet. Okay, now already we know that the sheet which gives the electric field lines which are the parallel lines and they are equidistant from each other. So it gives a uniform electric field like this. Okay, now here I place some area. So this is my area A, so which is at the distance r1. Okay, now I place this area here. Okay, so now this is at the distance r2. Now I place this area at r3 distance. Okay, so now there is no change in the field lines which are passing through these areas. Here we are here only two lines are passing through this area. Here also only two lines are passing through this area. Here also only two lines are passing through this area. So that's why the number of field lines which are passing through this area is same at every point along the axis, along the same axis. So that's why at every point on the same axis of those, so here for the particular area we are getting the electric field is same if it is a infinite charge compared to the r. Okay, so that's why if so here the magnitude of this is the magnitude. So the magnitude of the E, that is the electric field which is due to sheet, is sigma by 2 epsilon r. Now here we have to get the direction also. Okay, so direction of the electric field is what? Here this is the direction. So this is the direction, this is the direction, this is the direction of the electric field. So direction of the E field is always normal to surface. So that is normal to sheet. Normal to sheet. Okay, so this is about the applications of the Gauss theorem. So that is for the point charge and also the for the charge distributed on the long straight conductor and the charge distributed over the sheet. We are having another applications also, the charge distributed through the shell and also sphere. So for the conducting sphere means shell. Okay, conducting sphere means shell, non-conducting sphere means it is a sphere. Okay, so for a conducting sphere, inside there is no charge. Okay, charge is equals to 0 inside, so that is shell. Okay, if there exists a charge inside, so then that is the sphere. Okay, so we are having another two applications, that is the electric field which is due to shell and electric field which is due to sphere also, but those are not in our syllabus. So thank you.